All right, we are starting chapter 4. And in chapter 4, we're going to be starting our hypothesis testing. So before we start hypothesis testing, we have to really talk about what are we doing? So when we don't, we've been talking about Z distributions and Z scores, and we're going to be introduced to a new table this chapter called the T-table. So what we have been looking at in past chapters is mean and standard deviation when we know the population values. Now, most of the time in statistics, we don't know our population value. That's why we're doing hypothesis testing, so we can take lots of samples from the population, really gather good data, and then make inferences about the population. So we're going to use our T-table. Our T-distribution really relies on sampling data when you don't know the population values. So if you notice here, we have confidence levels up at the top. So as we become more confident, our degrees of freedom or our distance away from the sample mean becomes larger. So as we become less confident, our critical values become closer to the sample mean. But we're going to land in our on-ramps course in this 95% column. So if you want to put a box around that, just to let yourself know that we're going to be using values from this column. And so you see here we have degrees of freedom on the left-hand side. Our confidence talks about one-tail and two-tail test. So you can see that there. We're mostly going to be working with two-tail tests here, where our measure here is 0.05, and we're going to be calculating a 95% confidence interval. So you can see here, our confidence level here looks like this. This means that whatever our t values are on either side, we're saying we're 95% confident that our true population mean is going to lie in those values. So I'm going to put up some of our vocabulary terms for this unit. One is confidence interval. It's just an interval estimate for an unknown population parameter, and we state our confidence interval as a lower number and an upper number, kind of how we were doing our empirical rule intervals, and we're usually going to be at the 95% confidence level. Here we have margin of error. So I think when you have a sample mean, you know that because of natural variation and sampling error, that there's going to be some variation because of our sampling. So when we get our sampling mean or our sample mean, we know that there's going to need to be a buffer around that sampling mean when we're trying to estimate what the true population value is. So that's that margin of error. It's that buffer on either side of our sampling mean that allows us some room for sampling error, right? That natural variation. So in order to our margin of error here, we usually add and subtract that from our sample mean in order to find our confidence interval, and we'll be calculating that today. Our T distribution, it's the probability distribution used for unknown populations. That's this distribution table here. And we're going to be looking at that 95% column. Degrees of freedom allows for unknown values in the population. So if we can have a sample mean from that sample, we use n-1 because that last one value has to be that set value. So we calculate degrees of freedom using n-1, where n is represents your sample size. Your t-critical value acts as a cutoff point for determining statistical significance. So our t-critical value is what you'll be finding in this column here. So depending on your degrees of freedom, your t-critical value will be one of the numbers that aligns with the number of degrees of freedom that you have. All right, so let's start filling out our notes according to this paper here, looking at confidence intervals. So a confidence interval gives a lower and upper bounds. So when we gather our sample and we want to estimate what that population mean might be, we have to know a few things. We have to know our sample mean here. And then this calculation is our margin of error. So it's that buffer around the sample mean that allows us, it's an over-under, right? So I don't know if you're going to score exactly 30 points, but it could be over or under 2 points. So you could score between 28 and 32 points. X bar, this is just a review of what these symbols mean, is our sample mean. Our T critical value, that's what this is called, T critical value. And we get that from the table. So I'm going to give ourselves a note here from table. This is our sample standard deviation. And then this is our sample size. So square root of our sample size. N represents sample size. All right, so let's just practice using our table here at the bottom of our page. We're going to find the T critical value using the T distribution. So think T critical value is the number of standard deviations away that we want to calculate, right? So it says to estimate the mean weight of all cats in an animal shelter, you take a random sample of 10 cats. So here, if our N value equals 10, then degrees of freedom equals N minus 1. So N minus 1, we'll plug in 10, so it's 10 minus 1, so our degrees of freedom equals 9. So this is the number that I'm using to look on my table. So I'm going to follow down for 9 degrees of freedom and follow over to my 95% confidence interval level, and it's 2.262. So my T critical value is 2.262. All right, to calculate confidence interval for the mean height in inches of all students at your school, you randomly pick 30 students from your school to measure their height. So let's find our T critical value here. So our N equals 30. So degrees of freedom is N minus 1. So 30 minus 1. So our degrees of freedom is 29. Obviously, you can do that in your head. I just wanted to write it out for you. So I'm going to look on my table. What is my T critical value when my degrees of freedom are 29? It's 2.045. So notice that as my degrees of freedom increase, my T critical value decreases. That's because, think about a sampling distribution, right? In our central limit theorem, as our sample size increases, we become more sure or closer to our true population mean. So we become more precise and more accurate. So that allows us to give a more precise number when we have a larger sample size, right? All right, last 2 questions here. What critical value of T would you use with 10 degrees of freedom? Well, they've already calculated our degrees of freedom, so it's 10. So let's look at our table where it's 10, it's 2.228. So our T critical value is 2.228. All right, last one. What critical value of T would you use with 100 degrees of freedom? So this is probably going to be pretty small because that's a very large sample size, right? So if our degrees of freedom is 100, I'm going to use my table to go to my column here, 1.984. So T critical is 1.984. So again, notice that as we increase our sample size from 9 to 100, even though I'm still at 95%, I can be more precise when my sample size is larger, right? Because it's going to be closer to that actual population mean. Okay, let's flip it to the back here and we'll try this out in an example. So we wanted to know if the bags of potato chips we're buying contain correct weight of chips compared to the list weight on the bag of 42.5 grams. So this is our claimed value. The student collected the sample of 30 bags of chips and weighed each bag. So we know 30, this is N is 30, right? And the average weight of the bags collected was 40 grams. So that was our sample mean was 41 grams and a standard deviation of 1.6. So that was our sample standard deviation of 1.6. So what is the margin of error? Well, let's calculate some of these things. First, I need to find my t-critical value. Well, in order to get my t-critical value, I need to find my degrees of freedom. So my degrees of freedom are n minus 1. So it's 30 minus 1, or 29. So I'm going to look on my chart at 29 degrees of freedom. So 29 here, and my t-critical value is 2.045. So we're going to be using that 2.045 to calculate our confidence or our margin of error and then apply it to our confidence interval. Standard deviation, it tells us here, is 1.6. And our n value was 30. So we'll plug that in. All right, so margin of error is this one part right here. So it's our t-critical times our standard deviation divided by the square root of n. So we have, I'll just write our formula down here, t-critical times standard deviation divided by square root of n. So we'll plug in 2.045 times 1.6 divided by square root of 30. And if you calculate that, you're going to get 0.597. All right, so our confidence interval is taking this margin of error and adding and subtracting it to our sample mean. So our sampling mean was 41 grams, right? So we want to take 41 grams and subtract 0.597 to get our lower bound. So that would be 40.9403. And we're going to add it 40 plus 0.597 to get our upper bound. So our upper bound is 41.0597. So that's our upper bound. 41.0597. Oh, it's 0.0597. Wait, let me calculate that again. Let me go back to my calculator. All right, so we want to calculate this. Feel like I'm off on a decimal here. 2.045 times 1.6 and square root of 30. It is 0.597. Okay, so let's see. 41 minus 0.597. I feel like I'm off. I am off. Well, isn't this dandy? All right, so let me adjust. I feel like this is wrong too. Okay. I don't know what I was doing. 403. All right, and then this one is 597. Sorry about that. I had an extra number in there. All right, 403. It's okay to make mistakes, right? Just catch it. Okay, so now we have our confidence interval. So what this confidence interval is saying is that because we've gathered 30 bags of chips and we have our margin of error, so it's that buffer for sampling error, right? So we got the sampling mean of 41. However, with our buffer, our margin of error, we believe, we're 95% confident that the true mean value of the grams in a bag of chips would be between 40.403 and 41.597. So let's see what it says. Our claimed value was 42.5. So the chip manufacturer is saying that it should be 42.5, but that's not even in our confidence interval. Actually, that's way off of our confidence interval. So would you support this claim? I wouldn't. I would refute this claim because it's outside. Like 42 would be way over here, right? Or 42.5 where they claimed it. So our confidence interval here is I'm 95% confident, because that's the column that we chose, 95% confident that the true population, and we're doing mean here, of chip bags is between our lower bound 40.403 and our upper bound 41.597. So that leads us to believe that the chip manufacturer is not telling us the truth, or something went wrong with our sampling, right? So the population is not true, or something went wrong with our sampling, right? So you try the second one and check with me, and we'll do some more in class.